Welcome to this explainer. Today, we're going to unravel an everyday assumption you probably haven't even thought about since middle school geometry. We are talking about the circle. Every single day, in navigation, in construction, even in just basic math, we confidently state that a circle has 360 degrees. But have you ever actually stopped to wonder why? Like, is there some fundamental law of the universe that says a circle absolutely must be carved up into exactly 360 parts? Well, today, we're going to explore where this measurement actually came from and discover why modern mathematicians have completely ditched it for something way more elegant. So let's just dive right into this mystery. Why 360? Why not something, much simpler? Think about how we measure almost everything else in our modern world. We use a base 10 system. The metric system is perfectly, cleanly divided into tens, hundreds, and thousands. It feels logical, right? It's intuitive. So why on earth, when it comes to a shape as pure and fundamental as a circle, do we suddenly switch gears to 360? Well, as one mathematician bluntly put it online, our standard measurement is entirely made up. It's essentially a prehistoric habit we just never bothered to shake. There's absolutely no foundational law of physics dictating a 360-degree circle. It is literally just an inherited tradition. But to understand why we're so stuck with it, we've got to figure out who started the trend in the first place. To find the actual culprits, we have to travel back thousands of years. This brings us to Section 1, Sumerians and Base 60, the ancient origins. Way back around 3100 BC, the ancient Sumerians invented a base 60 counting system. You might hear this called a sexagesimal system. This mathematical framework was then passed down to the Babylonians in the 3rd millennium BC, and much later, the Greeks adopted it for their foundational work in geometry. They didn't count in neat blocks of 10 like we do today. They counted in 60s. Now, the secret here lies in just how useful their system was. You see, our modern base 10 system is actually kind of rigid. The number 10 is only cleanly divisible by 2 and 5. That's it. But that ancient base 60 system, it was highly composite. The number 60 is beautifully divisible by 12 different factors. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. This made it unbelievably easy to divide an hour or a circle into nice, neat pieces without having to deal with messy fractions. And it gets better. When you take that base of 60 and multiply it by 6, you get 360. The absolute game changer here is that the number 360 has exactly 24 different divisors. Just think about that for a second. If you're an ancient person trying to calculate something without a computer, without a calculator, heck, maybe you're just using tally marks on a wet clay tablet, having a number that can be divided evenly 24 different ways is an absolute dream. But convenient fractions are really only half the story. That brings us to Section 2, the astronomy connection. Look to the skies. For early civilizations, keeping track of the stars was everything. Ancient calendars, going all the way back to the Babylonians, actually estimated a year to be about 360 days, based on the cycles of the moon. They noticed that as the Earth orbits, the sun appears to move along its path by about 1 degree every single day. On top of that, Babylonian mathematicians really loved equilateral triangles. They would divide 6 of these triangles into 60 parts each, which naturally gave them a 360-part circle. So you combine a 360-day calendar estimate with base 60 geometry, and suddenly 360 makes perfect logical sense for tracking the seasons. So 360 is basically a very clever ancient approximation. But what happens when modern math needs something exact? Let's get into Section 3. Enter the Radian, modern math's choice. Here is the massive plot twist of our story. Modern mathematicians actually abandon degrees completely. Yep, they throw them out. Instead, they use something called the radian. A radian is defined as the angle you get when you take the exact length of a circle's radius and physically wrap it perfectly along the circle's outer edge, the circumference. If you translate that back to our ancient Babylonian degrees, it comes out to roughly 57 degrees. But the absolute beauty of the radian is that it ties the angle directly to the physical length of the circle itself. This completely changes how we visualize a full circle. Imagine a watch face, but instead of marking 360 degrees, a full revolution is exactly 2 pi radians. Half a circle is exactly pi radians. A 90-degree right angle? That's pi over 2. By using 2 pi radians for a full circle, we are seamlessly linking the angle's measurement right back to the universal formula for the circumference of a circle, which we all know is 2 times pi times the radius. It just clicks perfectly. Now, you might be thinking, okay, that's a neat little geometry trick, but why rewrite the whole rule book? Let's find out in Section 4 why radians rule math, physics, and beyond. Simply put, by using radians, real-world physics calculations become effortlessly easy. Take rotation speed, for example. Because the radian ties the angle directly to the length, finding the speed of a spinning wheel is trivially simple. You literally just multiply the wheel's radius by the number of radians it turns per second. That's it. So if you have a wheel with a 2-meter radius and it's turning at 6 radians per second, its speed is exactly 12 meters per second. Imagine trying to do that math in your head using 360 degrees. And this mathematical elegance extends right into graphing. Think about the famous sine and cosine waves. Radians are the absolute secret to graphing these trigonometric functions accurately. If you try to map out these waves using ancient degrees, the horizontal axis would have to be massively stretched out to fit all 360 marks, completely distorting the natural curve. Radians keep the proportions pure and true to the geometry of the circle. This visual purity leads us right to the doorstep of calculus. There is this beautiful, foundational relationship in math. The gradient, or the exact steepness, of the sine function at any given point is perfectly equal to the value of the cosine function. And conversely, the gradient of the cosine function equals the negative value of the sine function. It's a foundational pillar of calculus. But here's the catch. This is strictly true only when you measure your angles in radians. If you plug degrees into these elegant formulas, the whole thing completely falls apart. Because of radians, mathematicians are able to unlock other perfectly clean numbers too. For instance, if you calculate the area trapped under one of those graceful looping curves of the sine wave, it equals a neat, exact 2. Not a messy fraction, not some endless decimal, just 2. And once again, this incredible mathematical harmony only exists because we are speaking the language of radians. All right, let's move to our final point. Section 5, spherical geometry, mass on a sphere. Because the world isn't flat, right? We all learned that in flat geometry, the 3 angles of a triangle always add up to 180 degrees. But if you draw a triangle on the surface of a sphere, the angles actually add up to more than 180. If you want to calculate the area of that spherical triangle, there's an incredibly simple formula. The area equals the sum of its 3 angles minus pi. But yep, you guessed it, this elegant formula completely breaks if you try to use Babylonian degrees. It demands radians. Whether you are mapping a theoretical triangle onto a perfect unit sphere or you're literally just stretching strings over your breakfast grapefruit to measure the surface, mathematicians rely on radians. Why? Because radians are the actual natural language of shape, space, and motion. They're inextricably linked to the physical reality of the radius itself. So, it turns out that 360 is really nothing more than a highly divisible, 5,000-year-old calendar hack, perfectly suited for ancient accountants working without calculators. Modern math moved on, discovering that the universe actually operates on the elegant logic of pi and radians. But this begs a pretty fascinating question. If we are still out here stubbornly carving up our circles and navigating our ships based on prehistoric clay tablet habits, what other everyday measurements in our lives are just arbitrary echoes of the ancient past? Thanks for joining me on this explainer, and I'll let you chew on that one for a while.